Hi everyone, welcome back to my videos. I like to do a tutorial on areas in parallelograms and in triangles. So let's start off with our first theorem. Given parallelogram ABCD, prove that the area of ABCD equals base times height. So write down what we know, parallelogram ABCD, and I'm going to draw segment AN perpendicular to segment CD, right? We know that, given a line, so if you extend CD as a line and a point that's not on the line, we can draw exactly one perpendicular segment to this line, right? So we can indeed do this, draw the segment AN that's perpendicular to segment CD. And then we're going to draw segment BM parallel to segment AN. We're going to use a parallel line postulate for that, right? So we have this segment AN, and we have this point B, and then I'm just going to draw the parallel to segment AN. So it's going to be the same length, too. So, okay, and then we're going to extend segment CD to point M. Point M is where, the extension of segment CD intersects segment BM. And we know that segment BM is going to be perpendicular to segment CM. And we know this because if one of two parallel segments is perpendicular to a third segment, then the other parallel segment is also perpendicular to the third segment. So we know that segment AN is perpendicular to segment CM. We know that segment AN is parallel to segment BM. So since segment AN is perpendicular to segment CM, we know that segment BM is also going to be perpendicular to segment CM. We know that segment AC is congruent to segment BD because opposite sides in a parallelogram are congruent. We also know that segment AC is parallel to segment BD because opposite sides in a parallelogram are parallel. If we look at angle ACN and angle BDM, well, we can see that they're actually corresponding angles, right? If we take, segment CM as a transversal, right? Then these two, and we're considering segment AC and segment BD as these two parallel segments, then angle C and this angle D over here, they're on the same side of the transversal, and one's in the interior region bounded by these two segments, AC and BD, and the other is outside that bounded region. So indeed they are corresponding angles, and since AC segment is parallel to segment BD, then the two corresponding angles are congruent. Okay, we also know that angle ANC, this angle is going to be congruent to angle BMD because we know perpendicular segments meet at right angles, right? And all right angles are congruent. So we can apply the angle side postulate to get triangle ACN is congruent to triangle BDM, right? Because we know length of AC and we know the corresponding length of BD, so these two sides are congruent, right? And then we know angle C and its corresponding angle D are congruent, and this angle N and its corresponding angle M are also congruent. So that's how we apply the angle side postulate. So we know if the areas of two congruent figures are equal, right? So we know that triangle ACN and triangle BDM are congruent figures, right? So their areas are going to be equal. Area of triangle ACN equals area of triangle BDM. And we can use the reflexive property of equality. So area of ABND, this looks like a trapezoid, right? So its area is going to be congruent to itself. That's just a reflexive property. And then I'm going to use the addition property of equality. Area of triangle ACN plus area of ABND is equal to area of ABND plus area of triangle BDM. So in other words, area of ABCD is going to be equal to area of ABNM. So we know that segment AB is parallel to segment CD, right? Because opposite sides in a parallelogram are parallel, right? And we know that segment NA is going to be perpendicular to segment AB, right? Because if we take these, okay, so we have these two parallel segments, right? And we know that segment AN or segment CD is perpendicular to segment AN. So since segment AB is parallel to segment CD, then segment AB is also going to be perpendicular to segment AN, right? If one of two parallel segments is perpendicular to a third segment, the other parallel segment is also perpendicular. In the same manner, we're going to show that segment MB is perpendicular to segment AB. So we're going to use the fact that segment AN and segment BN are parallel to each other, and we just showed that segment NA is perpendicular to segment AB. So since segment MB is parallel to segment NA, then segment MB is also perpendicular to segment AB. So we have these right triangles, not right triangles, right angles, NAB, this angle here. ABM is also a right angle. ANM is also a right angle, and BMN is a right angle. So if we look at this quadrilateral ABNM, it has 4 right angles. Well, that's the definition of a rectangle. So ABNM is a rectangle, and we know from our last video that the area of a rectangle is equal to base times height. So we know that area of parallelogram ABCD is equal to area of rectangle ABNM. So the area of parallelogram ABCD is going to be equal to base times height, which is the same formula as the area of a rectangle. So next I'm going to derive the formula for the area of a triangle with an acute angle. You could do, I didn't include it for the obtuse case for angle C, but you can work on that on your own. It's it's going to be a similar proof. So let's just take a look at it. So we're given parallelogram ABCD, and we're given acute angle C. So acute, remember, means it measures between 0 and 90 degrees. Prove the area ACD, so that's the triangle, right, is going to be 1/2 times base times height. So we can start off by writing down that ABCD is a parallelogram, and we know that the area of a parallelogram is base times height. We're going to draw segment AD, right, and we can do that because we can draw a segment between 2 points, right? And segment AC is congruent to segment DB because opposite sides in a parallelogram are congruent. Segment CD is congruent to segment BA because opposite sides in a parallelogram are congruent, so we're using the same property here. And we know that segment DA is congruent to segment AD by the reflex property congruence. So we can use the side-side-side postulate to deduce that triangle ACD is congruent to triangle DBA. So the area of triangle ACD is equal to the area of triangle DBA. The area of congruent figures are equal, right? So we don't actually know what the area of the triangle is, right? But we do know that the area of ABCD is going to be base times height, right? So by using 7 and just plugging into this formula, area of ABCD equals area of triangle ACD plus area of triangle DBA, which is just the area addition postulate. We get area of parallelogram ABCD is equal to 2 times the area of triangle ACD, and then we can just divide by 2 on both sides to get area of triangle ACD is equal 1/2 times area of ABCD, And we know the area of ABCD is base times height. So area of triangle ACD is equal to 1/2 times base times the height. And that's going to be our formula for finding areas for triangles. So let's go on to our next slide here. Example 1. So in this case, we have an obtuse angle, right? So the obtuse angle is going to be C. So obtuse means that the measure of the angle is between 90 degrees and 180 degrees. So measure of angle 1, this angle here is 30 degrees. Measure of angle 2 is 90 degrees. Segment AB has length 18 and segment BC has length 10. And we want to find the area of triangle ABC. So what can we do? So we write down what we know. We know that the measure of angle 1 plus the measure of angle 2 plus the measure of angle BAD is going to be 180 degrees, right? Because the sum of the measures of the angles of a triangle is 180 degrees. So if we look at this larger triangle ABD, right, we get this kind of property here. So we can substitute and get measure of angle BAD is equal to 60 degrees, right? Just plug in measure of angle 1 equals 30, and measure of angle 2 equals 90, and you just simplify it. So we know that triangle ABD, this larger triangle, is a 30, 60, 90 triangle. And we know that a 30, 60, 90 degree triangle has the lengths of its sides are going to be in the ratio 1, square root of 3, and 2. So we know that AB, which is the hypotenuse, is 18, right? So if we divide it by 2, then we get the length of AD, right? AD is the smallest size. So if you have 9, and then AD is going to be 9, and AB is going to be 2 times 9, which is 18, which we have. So now we know the height of the triangle is 9, and we know the base is going to be the length of BC, not the length of BD, because we're only interested in this triangle here. So we can use the formula for the area of a triangle. Area of ABC equals 1/2 times base times height, and then we can just substitute area of ABC is 1/2 times the length of BC times the length of AD, and then you do that and you simplify to get 45. Okay, example 2. Given triangle ABCD is equilateral and each side has length L, find the area of triangle ABC in terms of L. So we write down what we know, and we know that the measure of each angle of an equilateral triangle is 60 degrees, right? So what I'm going to do is I'm going to draw altitude AH, right? And altitude AH is going to be perpendicular, right, to the opposite side BC. So measure of angle AHB is 90 degrees, right? Because an altitude meets at right angles with the side to which it is drawn, and right angle measures 90 degrees, right? So measure of angle B plus measure of angle AHB plus the measure of angle HAB. I'm sorry, did I say that right? So measure of angle B plus measure of angle AHB plus the measure of angle HAB, yeah, is going to be 180 degrees, because the sum of the measures of a triangle measures 180 degrees. We're looking at this triangle ABH. So we know that measure of angle B equals 60 degrees, measure of angle AHB equals 90 degrees, so measure of angle HAB equals 30 degrees. So triangle ABH is a 30, 60, 90 degree triangle, and we know that a 30, 60, 90 degree triangle has this ratio 1 square root of 3, 2 for the lengths of its sides, right? So AB is going to be equal to L, right? Because each side has length L. So the shortest side, BH, is going to be L divided by 2, right? And AH is going to measure L divided by square root of 3. So now let's take a look at BC. So this is a theorem. An altitude of an equilateral triangle is also a median. And then we use the definition of a median. So you can actually prove this. I'm not going to actually do the proof to show this, but that's actually a good exercise to do on your own to show that the altitude of an equilateral triangle is also a median. So a median, so that means H is going to be the midpoint, right, of BC. So in other words, length of BH is going to be 1/2 the length of BC. So length of BC is going to be 2 times BH, which is equal to L, which we already knew, by the way, just from up here. But, I thought that this would be a good kind of thing to throw in there since, we can use these theorems about triangles. So anyway, area of triangle ABC equals 1/2 times space times height. And area of ABC is going to be 1/2 times L times the height. The height is going to be the measure of length AH, which is L divided by root 3. So you simplify and you get square root of 3 times L squared divided by 4. So let's go on to example 3. We're given a parallelogram ABCD. We're given the measure of angle D equals 120 degrees. We're given that segment AH is an altitude for ABCD, and length of AC equals 4 and length of CD equals 10. Find the area of ABCD. So we write down what we know. We know that angle C is supplementary to angle D because consecutive angles in a parallelogram are supplementary. So the sum of the measures of supplementary angles is 180 degrees. So measure of angle C plus measure of angle D equals 180 degrees. So if we plug in measure of angle D equals 120 degrees into this equation in 7, we get measure of angle C equals 60 degrees. We know that segment AH is perpendicular to segment CD because an altitude is perpendicular to the side to which it is drawn. We know that the measure of AHC, this angle, is going to be 90 degrees because perpendicular segments meet at right angles, and right angles measure 90 degrees. So if we look at triangle ACH, if we sum the 3 angles, we should get 180 degrees, right? Sum of the measures of the angles of a triangle is 180 degrees. So then if I substitute measure of angle C equals 60 degrees and measure of angle AHC equals 90 degrees, we get measure of angle CAH. This angle is going to be 30 degrees. Therefore, triangle ACH is a 30, 60, 90 degree triangle. So we have this ratio, right? 1 square root 3, 2 for the lengths of the sides of this triangle. So AH, the length of AH is going to be AC divided by root 3. And if you simplify this, you get square root of 3 times AC divided by 3. So now we can find the formula, using the formula for the area of a parallelogram, area of ABCD equals base times height. So in other words, length of CD times length of AH, right? We know that CD equals 10, and AH is going to be, well, what's AC? AC is 4, right? So this is going to be 10 times 4 times square root of 3 divided by 3. So that's all I have for you tonight on areas. So please look over my notes. I hope you learned something tonight, and I look forward to seeing you during my next tutorials. All right, have a great night, everyone. Bye.